Hello everyone, and welcome to Office Hours with the Meter Environment team. Today's session will focus on soil moisture measurements, and we're shooting for about an hour of Q&A with our experts Leo Rivera and Chris Chambers, whom I will introduce in just a moment. But before we start, one housekeeping item. If you're watching this video and you think of a question you'd like to ask our science experts, we encourage you to submit your question on our website at metergroup.com. And someone from our science and support team will get back to you with an answer via email. All right, with all of that out of the way, let's get started. Today our panelists are application specialists Leo Rivera and Chris Chambers. Leo operates as a research scientist and director of science outreach here at Meter Group. He earned his undergraduate degree in agriculture systems management at Texas A&M, where he also got his master's degree in soil science. And there he helped develop an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Currently, Leo is the force behind application development in meters hydrology instrumentation, including the SATURO, HYPROP, and WP4C. He also works in R&D to explore new instrumentation for water and nutrient movement in soil. Chris Chambers operates as the Environment Support Manager and the Soil Moisture Sensor Product Manager here at Meter Group. He specializes in ecology and plant physiology and has over 12 years of experience helping researchers measure the soil-plant atmosphere continuum. So, thanks for joining us, guys. All right, let's get started taking some questions. This first question here today is, how difficult is the calibration of dielectric sensors?
I wouldn't call it difficult. It's more like just kind of a process to work through, right?
Mm-hmm. Yep.
Basically any soils lab, most science labs across the country are going to have everything you need, which is a drying oven, a precision balance, and
Soil.
That's pretty much it, right?
Pretty much.
Okay.
Soil and water. Yep.
So difficult it is not. There are some pitfalls that can lead to bad data.
Yep.
And we have a standard operating procedure that we use. We share it online. You can go to metergroup.com and search for calibration, and our procedure will come up. And we've been doing it for a long time. We're pretty good at it, but it's not a secret. Everyone should be able to do it.
Yeah. No, I think the biggest challenge that people run into is following bad methods when it comes to calibrating your sensors. And of course, really the big question is, what are we trying to ultimately get the outcome of? Because we're talking about calibrating dielectric sensors, but the goal is to take our dielectric measurement and convert that to a volumetric water content.
Or capacitance measurement.
Capacitance, yep.
Whatever your technique is.
Yep, whatever your approach is to get that. But our goal is to convert that to a volumetric water content. And one of the big challenges that I often see is, if you look in the literature, people not homogenizing the soil, getting a good evenly mixed water content within the soil, because you have to remember what your sensing volume actually looks like in the sensor. Or I see people doing field methods where they're trying to calibrate in situ, which is even more challenging because it's so much harder to control things and actually get a proper reference measurement.
Now let's go a little bit further down this rabbit hole, because the rationale, no, seriously, the rationale behind doing these is because they want to mimic the soil structure, right?
Yep.
Which, if you're going to homogenize it, you totally destroy the structure.
Correct.
B, and to get what people will actually see in the field from a satellite, right?
Yeah.
That's why they want to use those two methods.
Yep.
And so what do you think the trade-off is here? Why does the homogenized method give you so much, make it worth sacrificing that, especially the structure for?
Yeah, I think that's a great question. I mean, ultimately is what is going to be our bigger source of error in the calibration? And also, what is our ultimate, why do we do soil-specific calibrations? What are the pieces that we're trying to correct for in that soil-specific calibration? And when you look at the things that primarily impact the water content measurement, structure plays a role.
But density is your driver.
Bulk density and the soil texture itself. And especially if it's most mineral soil calibrations from manufacturers perform fairly well. But oftentimes you might wind up in a site that has unique characteristics that you're trying to calibrate for.
Or you can almost always improve on the factory calibration at least a little bit.
Yep. But you don't want to improve by using a bad calibration.
No, exactly.
Yeah,
and we've seen that happen before.
Absolutely.
So know your bulk density of the field.
Yep.
Right? Because you're going to want to, if you use the homogenized method, you're going to want to pack back to that density.
Correct.
And the real reason why we recommend the homogenized method is because if you get like wetting fronts or drying fronts in an intact core or in a soil, right?
Yeah.
So you have an inherent spatial variability in your core from reading to reading, right?
Yep.
And that is what frequently leads people astray because you're weighing this entire thing, assuming it's homogeneous,
Yep.
but it's not. And your sensor may be detecting something different than what you're actually verifying with your gravimetric sample.
Yep. Exactly.
And that's where we've seen horror stories.
Yes.
Our next question here, they are asking, can you discuss how soilless organic media, such as biochar or coco coir, affects dielectric sensor accuracy? Does the physical shape and size of the pores holding the water being measured affect the measurement since it affects the electrical path between the anode and cathode?
Yeah. I think that anode and cathode reference is probably more so in line with resistance-based measurements, which isn't completely accurate for all sensors, but I'm probably digressing into something that's not really.
Well, no, I think it is. I think it is relative.
Yeah.
Because try not to. When you think of anode and cathode, what comes to mind is a one-directional flow of electrons, right?
Yep.
Kind of. That's kind of the mental model that comes to my mind, anyway.
Yeah.
And the sensors are emitting an electromagnetic field and alternating the charge at a high frequency, right?
Yep.
So that electromagnetic field in the soil is kind of the key, and it is affected by the substrate that it's in, the amount of water content in the soil. So it does change the shape, but it's in the end it comes down to kind of a sampling question, doesn't it?
Yeah, I think it comes down to a sampling question. I also do think there is, depending on, especially, let's say you're amending soil with some of these materials, like biochar especially. There's two things that happen with that. One, biochar inherently has a different dielectric permittivity than soil. And if I'm not mistaken, when you amend with biochar, sometimes you bring along some solutes that come with that can increase the electrical conductivity. So depending on your approach, you could see some issues there. But really, I think ultimately it comes down to what the dielectric permittivity of the material is that you're adding, and if that differs a lot from soil.
And if your sample is representative of how you're going to use the data, install the sensors in the field, as long as that's representative, then you're going to be in good shape. We do recommend a custom calibration with biochar or coco coir because it will be very different than a mineral calibration and probably different than a factory soilless calibration.
Yeah. And I think just to dive deeper into this question, I don't think it really has anything to do with the physical shape or the size of the pores that are created by these different materials. That because we're creating an electromagnetic field, those don't really govern how the electromagnetic field behaves, but it's really ultimately comes down to the properties of the material itself, and the dielectric properties of the material.
I hear there's more and more commercial biochar products out there, so it's probably something we'll see more and more of.
Yep, it's true. Yeah, it'll be interesting to see where that continues to go.
Next question is about tensiometers. They're asking, can they measure the potential difference between 2 points with millimeter precision?
The difference between 2 points in millimeter precision. This kind of it's kind of inherent in the accuracy of the sensor, right?
Yeah.
It's really dependent on how precise your tensiometer is.
Yep.
So what is the accuracy of, let's use a T5 here as an example.
So
not a T5.
TEROS 31.
TEROS 31.
Yeah.
Thank you.
Great question. So the accuracy, resolution is 0.1 hectopascals.
Right.
1 hectopascal is equivalent to 1 centimeter of tension,
Which
or water potential.
Which is a tenth of a kilopascal? A tenth of a kilopascal.
A tenth of a kilopascal.
All right.
So
we're going to do math on the fly here. This could get ugly, folks.
So
bear with us.
in terms of resolution, you could resolve kind of to that millimeter, but your accuracy of these sensors is about half a hectopascal, I believe.
So especially if you're comparing 2 points.
Yeah.
If you're comparing 2 points, the error bars overlap, and you really can't separate those two.
And I don't really know anything that would measure to that type of precision in soil. But my question is, do you really need that level of precision if you're trying to govern water? If you're trying, and ultimately it comes down to what your goal is. Are you looking at fluxes? And you're trying to look at water movement in the soil? Absolutely. I think potentiometers can give you the precision that you need.
Or at least give you the best answer possible.
Yep. Yeah, out of anything that you're going to get. Now, if you're looking at making these matrix potential measurements with something like a TEROS 21, which is a solid matrix sensor, I wouldn't do it.
Nope.
You don't have the resolution or the accuracy that you need to make that, especially when you're talking about those small changes in looking at water flow. That's not something that's going to work well for that. But tensiometers are the best tool available to try and infer these things that might happen in the soil when it comes to looking at water movement.
Next question. How much can organic soil amendments influence soil moisture?
Quite a lot.
Yeah. It depends on what you're adding to the soil and also how long it stays before it degrades.
Its distribution in the soil.
Yep.
But let's just kind of unpack it and go into how they affect both water movement through the soil, which is interesting, and the soil moisture. Because we're looking at an effect on porosity, right?
Yep.
Generally, they're lighter than the density of. They're less dense than soils.
Yep.
So you could see higher saturated hydraulic conductivity, right?
Yep.
In general, more water holding capacity with the higher porosity.
Yep.
And in the end, a custom calibration is probably going to be a good idea for organic soil amendments, depending on how much you're adding.
Yeah, I think if you're adding more than 5% of the volume of soil, then it's probably something where you'd want to add. Look at a custom calibration. But there's a lot of ways that these different organic soil amendments, in fact, impact how water is retained in soil. There's quite a bit of literature on there looking at these different things. I mean, we see people spend a lot of time looking at that, especially looking at how it impacts the retention curve of the soil. It just depends on. It's kind of similar to our first question or an earlier question about the coco, coir, and biochar amendments type things.
Yep.
So,
question here: is it possible to determine the soil hydraulic characteristics, field capacity, permanent wilting point, KSAT, from soil water content readings?
No.
Yep.
Next question. Hey, you said yep.
No,
Are
I
we
said
disagreeing here?
No, I agree. I said no.
Is it yes or no?
No.
All right.
By themselves, no.
That's right. You need additional information.
Yep. If you can combine your water content with a water potential reading, then you can start to get at some of the things, especially field capacity, permanent wilting point, if you have those two measurements
Especially
together.
water potential. Okay, hang on here, because if you go to Methods of Soil Analysis, which is a key book, then there is a method for determining field capacity. Is there not?
Yes.
Am I wrong?
Yes, you're not wrong.
Okay. So... the point is, it's kind of subjective, right?
Exactly.
Because in that you're waiting for the soil to drain to a certain degree, right?
Yep.
It's something like water stops dripping out of your bucket or whatever.
Yep.
And I always found that terribly subjective. And like subjective errors are some of the worst ones to try and account for. Even if you have matrix potential, and your field capacity is at minus 35 kPa instead of minus 30 kPa, it's at least you're going to get a consistent reading out of that every time instead of a different water content at field capacity.
I also would put to question our traditional view of field capacity, but that's probably a bigger conversation than this this office hour session. But some of the one that is a more complex value to get at is going to be your hydraulic conductivity.
You need lots more information.
You need a lot more information. Now, having said that, if you have at 2 points, you have your water potential and your water content readings, and you know the distance between those 2 points, and you know your general fluxes of water, you can just use Darcy's equation to calculate your hydraulic conductivity and get a curve. But it is going to be prone to error, especially because hydraulic conductivity, a big part of that is flow through macropores, and oftentimes that is missed in some of these in situ measurements. So it can be challenging to do that in the field.
So soil water content alone gives you half of the water state picture.
Yeah.
Right. You've got the volume, which, with a little additional information, you can get the mass.
Yep.
Right. So we have the mass, but we're missing the energy state part of the equation, which is necessary if we're going to get those other values.
Yeah. Yep. So I think sum it up, you can try and get at some of these things through with these measurements. It's a lot easier if you have the water content and water potential measurements together. But also you need to understand where your sources of error from that will come.
Right, exactly.
All right. A basic introductory question here. Why is it important to find the volumetric water content reading instead of gravimetric water content? What does the volumetric water content reading mean? How does it help us in real life?
I don't think that's that basic.
I'm with Chambers. It actually is a more complex question than it comes off as.
Right.
Yeah.
The sensors, the reason why we work with volumetric water content a lot is because that's what the sensors give you. And the reason it's volumetric water content and not gravimetric is because the total volume that you're reading with the sensor is largely undefined.
Yep.
Right? So that volume that you're reading, that measurement volume of influence, can change a little bit when you put it in soil. When there's a capacitive load on it, it's going to shrink or get bigger. So, but we can measure the volume of water per unit volume of the soil. Yep. That's what we can do. Yep. So you kind of have to know the bulk density to convert back to gravimetric water content with that. Even though the mass of the water might be what we really, really want in many cases, the volume of water with in situ soil sensors is what we can actually measure.
Yeah. Yep. And this is an interesting question because depending on the industry that you come from, you actually might gravitate more towards gravimetric water content. Engineers tend to use gravimetric water content more than volumetric water content. But I would argue, this question I love the last part of this question. How does this help us in real life? Gravimetric water content by itself can be hard to interpret what it actually means because it has to be referenced to, you don't know how much mass of soil you have in an area, right? But you can always relate to, I know in this unit area, I have this volume of water.
And your inputs and outputs in the system are going to be in generally a linear water.
Yep.
So your precipitation, you're going to look at it in millimeters of water. Your drainage, you're going to look at in millimeters of water.
Yep.
So if you have centimeters of water, which is really easy to convert to millimeters of water in the system, then your storage is on the same unit scale as your fluxes.
Yeah.
And that's really convenient.
Yeah. The only area that I'll add that there can be some challenges with volumetric water content is in expansive soils that change volume. But that's a whole different...
expansive soils.
You got to remember that's where I spent a lot of time.
I know.
But the expansive soils bring about their own challenges that are well beyond
And they're
this
pretty
question.
common too, so you're going to encounter them.
Yeah.
Unless you live on the Palouse.
Yeah, everything works well and is easy on the Palouse. But ultimately, I think volumetric water content just gives you a much better reference to understand what water content means.
And if you have the bulk density, you can go back and forth between them.
Exactly.
Is there a soil temperature slightly above freezing that you would recommend using as a data quality threshold, or just use 0 degrees Celsius and then check if there were any remaining rapid drops in the volumetric soil moisture, dielectric observed that need to be filtered out as well?
Like the frozen soils, is that what we're talking about here?
Yeah, I think that what they're getting at is what temperature would you use as a QA/QC threshold for your water content
like temperature. I don't like using temperature at all for this.
Yep.
Why is that? Because
Chambers?
it's going to be slightly negative. The freezing point in soils.
Yep.
And you see this over and over. It's not going to be too negative. -2, -3. I think the lowest freezing point I've ever in the data sets that I've looked at are about getting close to -5.
Mm-hmm.
So generally your freezing point is going to be a little bit negative, and your water content, unless it's bone dry soil and there's very little water in there, it's going to be a pretty clear threshold for when your soils freeze. Unless you're in this middle state in between freezing, if you're during a state change, then things can get really messy and hard to interpret. If you have frozen soils, it's going to look like there's 0 volumetric water content, or there's going to be like 3 or 4% volumetric water content. It's going to be really dry.
Yeah. And the reason that freezing point shifts down is because of the solutes that are present.
The solutes in the soil surface.
In the soil, and that brings down the freezing point of the water, and that varies because you might have different level of solutes in different areas, at different soils, even at different times. So it is challenging, but like you said, it's pretty apparent when freezing occurs.
That's right.
Now after that, it can be a little dicey.
So state changes are always difficult. For this, using a temperature filter might be really handy just as a flag.
Yeah.
I think you could use 0, and if you get below 0, then just kind of flag the data to look at.
Yep.
But it's really hard to get. To nail that point down to this is frozen and this is not frozen, just from the temperature.
Yeah.
This individual is asking, is the TEROS 21 water potential sensor sensitive to temperatures? I found a strong daily change in TEROS 21 data in concert with temperature changes. Is there a possible way to correct the temperature effect?
I can start this one off. So, yes, we know that the TEROS 21, both the Gen 1 and the Gen 2, are sensitive to temperature, especially as the water potentials go lower. And there's 2 factors that impact that. One is the Gen 1, the sensor itself, the electronics were a little more sensitive to temperature changes. But the ceramic, as you get to lower water contents, there's less water in the ceramic. And so as temperature changes, you see a bigger impact from temperature on that measurement, on that matrix potential measurement.
But why is that important? Because, you get hardly any temperature sensitivity in the wet end.
Yep.
Between 0 and -100 kPa. You're going to see just tiny little squiggles.
Yeah.
Right? And then same temperature change at, say, -15 bar, and you could see 100 kilopascal swing.
Yeah.
For the same temperature. Now, explain that.
So I think there's a couple of factors. I mean, we talked about the sensor component, but the other piece is that water potential is a temperature dependent measurement. And so some of those things that you're seeing is actual temperature influence on water potential, matrix potential itself. But it's really hard to interpret that. And so there's a paper by Walther and Schleppe that does a pretty good job of normalizing that to a temperature that you can use. But if you can remove the sensor component of it, I think there's value in knowing what that pattern is, because we do know that water potential is is dependent on temperature as well.
And the soil water retention curve makes a difference there too, right? Because you're at a different region of the soil water, of the ceramic
Yes.
characteristic curve.
Yeah. Yeah. And so that there's a lot that goes into some of that.
One of the main things to remember with the TEROS 21 is that it doesn't measure matrix potential. It measures water content.
Yeah.
And so the relationship between water content and matrix potential for the ceramic, we have it really well characterized. Yeah. But a small change in water content at one part of the curve isn't going to be the same change in matrix potential, depending on the water level.
Yeah. Yeah. So there's definitely some challenge with that. I think there's still quite a bit of work to be done into understanding that. That Walter and Schleppe paper is actually a really great paper, and they do a really good job of coming up with some methods of handling that.
And of course, the TEROS 21 Gen 2 is so much better.
Yeah,
for that.
Yeah, and so that the other factor has been working on improving the electronics and the capabilities of the sensors to make those corrections, and it's something I think we're going to continue to push on as we continue to develop these sensors.
Good.
All right. This person's asking, what is the best method to correct for temperature sensitivity of sensors? Does the temperature correction depend on the measurement principle of the sensor? For example, time domain or frequency domain reflectometry, capacitance, resistance, etc.?
It's a great question.
Oh boy, there's a couple parts to this, right?
There is, yeah.
There's the effective temperature on dielectric itself.
Yep.
Right?
Yep.
That's pretty well characterized, correctable.
Yep.
And then there's the effective temperature on the electronics.
Yep.
And that's not, I don't think that's terribly technology dependent. What do you think?
The only way I think it's technology dependent is if the sensor has built-in correction for temperature or not. So for example, analog sensors typically are not going to have a built-in temperature correction on the measurement itself. Digital sensors, depending on the manufacturer, it's a lot easier to build that in. And so you'll probably find that most digital sensors have a temperature correction applied to the sensor.
The 5 most used sensors for research are going to have that.
Yeah. And so as long as you're using, the more commonly used research grade sensors should have a correction for that. So then it really just comes down to understanding the impact of temperature on water content itself and dielectric permittivity. But also, I think it also comes down to understanding that some of those fluctuations that you see could be daily fluctuations in water movement in the profile as well. And I think it comes down to looking at when your peak.
So hard to pin down, though.
It is, yeah. I mean, I always, if I'm looking at those data, I'm going to look at my peak in temperature and my peak in water content. If those coincide perfectly, it's probably more of a temperature dependence thing. But if there's an offset, then some of that actually has to do with those daily kind of hydraulic fluxes that happen as you get a pull on the water from evapotranspiration and then a relaxation in the evening that allows the water to kind of shift back down a little bit, which we have observed those type of data.
Do you have a flag? Like what % change in water content per degree C that sets you off? That kind of trips your...
Oh, that's a great question.
Alarm.
Probably... This is going to be just off the top of my head.
Totally put you on the spot.
You did, but that's great. I mean, probably more than per degree C.
Look at it over 10 degrees C.
Over 10 degrees C, probably 2% maybe.
That's pretty big, isn't it?
Yeah.
That'd be a red flag for me.
I think that would be a pretty big red flag.
In the TEROS
3%.
12. In the TEROS 12, maybe not the EC5.
Yeah. And that goes back to the analog versus digital sensor.
Exactly.
So, probably somewhere around that 2 to 3% range across 10 degrees C. Yeah.
All right. We've got a field question here. Are there installation strategies to avoid cracking around the sensor for clay soils? By the time the soil cracks, I would imagine it's too dry to reinstall.
On installation, if you're installing in August in a clay, it's going to be a rough day. I sympathize. It's just really hard to work around. If you're installing in dry clays and you see a crack, I think you should move to a different spot. You're probably not going to be able to there's just going to be the risk of having that crack right there.
Yeah.
It's less of a risk with our TEROS line of sensors than it was. It has less of an impact. It's much easier to avoid with TEROS than it was in our older sensors.
Yep.
But the real key here is not having any air gaps near your pins.
Yeah.
It's a little bit forgiving if you get further away from the sensor. When you look at it, think about the fact that air has a dielectric of 1 and water has a dielectric of 80.
Yeah.
So any cracks are just going to kind of push your soil moisture sensor data towards the extremes. Towards the low extreme when it's super dry, towards the high extreme when it's super wet.
Yeah.
When it's saturated. So try again. If you get a crack on installation, move it a little bit, either a different side of your borehole or a different part of your trench. But stay away from the cracks if you can.
Yeah. I agree with that. And I also think that one of the approaches that you can take to minimize, and I say minimize, you're not going to get rid of this issue. Shrink soils are a challenge no matter what. But minimizing site impact, so the site disturbance upon your installation really helps minimize that shrinkage. For example, if you dig a big trench to install your sensors, there's a big possibility that trench is going to experience a lot more volume change over time than some of that native soil might. And so the borehole method, that's why I love the borehole installation method, especially for these types of sites, is that it helps avoid some of those issues. The other thing is you're not always going to know, especially like in true vertisols where you have those slick and slides and the cracks that form from that shrink swell behavior. If you install in the wet season, you might not realize that you've installed on a crack. And so the best thing to do is have replication in those sites, because that way you can use that as a QA/QC for each other.
What do you think? Is it best to install in spring or fall then? Install when it's dry.
Personally, I would still say it's better to install in the spring, just because of the challenges of installing in clays outside of that period.
It's gonna go a lot easier on your gear. It's gonna go a lot easier on your sensors.
Yep.
You're probably gonna get better contact.
Yep.
And then it's just keep an eye open for signs of cracks developing.
And it is you can see in the data if that's occurred, because you see a pretty you can see like a really rapid change in water content that coincides with that crack opening. And when periodic wetting events come in, you'll see it's going to be really flashy. It's going to be a quick spike in water content and then a quick dip in water content.
You can see it in your data, but I've never once had the conversation with someone where it looks like a crack developed and they're happy, right?
No, they're not going to be happy.
It just doesn't happen.
Unless you're like me and you get excited by soils cracking.
Yeah.
Yeah, but no, it is.
Okay.
The only way to really for me, it's replication. Just the more measurements, the better, to help cover some of that variability that you're going to see from the soils cracking.
It's a good answer.
With a field of 100 meters square, how would you distribute and how many soil sensors would you consider to have reliable soil moisture data? What if there are two different soil types?
Now, this is a classic sampling problem.
Yep.
Regardless of the field size, it really comes down to soil type and hydraulic characteristics.
Yeah.
Right?
Yep.
And soil type doesn't quite capture it all. If you say two soil types, like you've got, just a clay in one spot and a blue silt loam in another spot, right? You've got two types, but they're going to behave very differently depending on their slope.
Yep.
Their, not so much their aspect, but whether you've got a high spot or a low spot, whether water's draining into it. So classic sampling problem, but not necessarily very easy to answer, because you have to capture the variability of your field to answer your research questions.
Yeah. It is. This is one of the more challenging questions that we get a lot. And it's hard to determine without having more background information on the site. One thing I do think that is promising is utilizing satellite data to try and characterize.
So identify beyond just the soil maps.
Yep. Yeah. Soil maps were super helpful. Getting your elevation changes, understanding your landform changes across that site, unless it's perfectly flat. But even then, there are things that happen below ground that you're not seeing at the surface.
That's right.
But satellite data actually, I mean, we're spending some time working on that. That's actually what we have some of the fellowship students that we're working with looking at. And that might be a powerful tool to use, but still you need background information to help make these decisions. It's just another form of background information.
Let's simplify this question a little bit. 100 meter squared field, and we're on a side slope. There's no top nor bottom. There's 2 soil types in there, so no hydraulic difference other than the 2 soil types, right? Let's simplify it a little bit. So minimum of 3, right? Because you're going to want to calculate a variance.
Yep.
So a minimum of 3 sensors in each soil type.
Yep.
So that you can capture the variability, because they will be different. So that's 6 sensors. How many depths? It depends.
It depends.
So this is where, if you want a profile, if you want to capture the different layers, and kind of where you put your deeper soils and your deeper sensors is going to depend on the soil type that you have and your soil horizons and the questions you're trying to answer. So you might want 3 sensors at your deeper depths in each soil type too.
Yeah. Or just use a profile probe and that's
Or just use a profile probe and then you get it all. TEROS 54.
Yep. Yeah. No, it's a tough one, but I agree with that. I think at least characterizing the 2 different soil types, I would still try to replicate a little bit across those soil types, maybe 2 to 3 replicates.
Right.
But it really depends on what you can do. That's not always feasible. So,
next question. If the input voltage of the sensor fluctuates, will this affect sensor readings?
That depends on your sensor. So we only have a couple of sensors now that I can think of that don't have voltage regulators.
Yep.
So something like the EC5, if you change the voltage input, it will change the voltage output.
Yep.
So keep a consistent input. That's our only soil moisture sensor for which the input voltage matters.
Yeah. I mean, there is an operational range that they need to be within, but as long as you're within that operational range, then it really shouldn't matter.
Yeah.
But if you do dip outside of that, then it will impact your measurement, even with the digital sensors, because the circuitry needs a certain input voltage to operate.
Yeah, that's right.
If you dip below that,
so if you go too low, it'll your data is going to be crazy.
Yep.
So you'll know.
Yep.
If you go too high, it's probably going to fry your sensor and break it.
Yeah. So just operate within the specs.
How much is the soil water content reading affected by soil texture? Is there a standard method to calibrate the soil water content reading for different soil textures?
Yeah. I mean, we talked a little bit earlier about soil-specific calibrations. There absolutely is methods for that. But really, it comes down, again, some of it actually comes down to the sensor that you're using and the frequency that sensor operates at. Some sensors we do find to be more sensitive, especially as you increase clay content. That's the main of the 3, sand, salt, and clay. When you increase your clay content, it can impact some measurement techniques.
Let's back up a little bit.
Yeah.
Let's just answer the first part of the question.
Okay.
How much is the soil water content reading affected by the soil texture? All the way. So you cannot interpret soil moisture data if you just have soil water content and no soil texture information. You can't.
Wow, that's
If
because
you don't
we're trying
know-
to interpret what soil water content means.
You don't know whether or not you have a sand or a clay,
Yep.
and you just have soil water content numbers, those numbers are going to be meaningless.
They're meaningless because there's no basis of what that means in terms of other things,
Exactly.
like plant available water and things like
Exactly.
that. Yeah. I absolutely agree with that. But when it comes to the sensor performance, it really depends on the sensor.
That's right.
Yeah. But yeah, for sure. This always comes down to background information, tying water content to something that's more meaningful, like plant available water. Those all play a role.
But it's going to be super helpful. It's going to be necessary for any treatment effects that you have.
Yep.
If you have 2 treatments and you don't know what soil type is in either one of them and they're different, then you're going to completely confound your treatments.
Yep.
So soil texture matters.
Metadata. Sorry. Metadata is super valuable in trying to interpret any type of data that you're reading. If you don't know the site, the characteristics, those are things, then those readings can be meaningless.
That's right.
So, yeah. We know that as you change there's 2 things that happen when you change your frequency of operation. You either get impacts from texture, it's clay content primarily, because it impacts how the water polarizes when you emit that electromagnetic field. Or if you go in the other direction, it's the EC. So some of then you become more sensitive to changes in the salinity of the soil. So it's about finding that sweet spot. A lot of the sensor manufacturers have spent a lot of time working on this, trying to develop tools for that. Some sensor manufacturers have different calibration equations for different soil types as well. So those are also good options. If you know you have a specific soil type, use the calibration that they recommend using for that soil type.
Exactly.
This looks like it is going to be our last question for the session. Can you build and trust water retention curves if you bury water content and water potential sensors at the same location and depth? Will it compare well with what one gets from the HYPROP?
That's a great question.
I love it.
Yeah, I absolutely think you can. And I honestly think there's even more information you get out of your in situ retention curves, especially when it comes to getting your scanning curves, than what you might get out of just the HYPROP measurement that is only on the drying leg of the retention curve.
And it's also, the HYPROP is also your ideal measurement, right? It's why you take lab measurements. You completely saturate it, which doesn't happen in the field. So it's pretty common to have like a field method and a lab method. And where the lab method is going to kind of get at the intrinsic values of your soil. Right? How your soil's effect on the soil water retention curve or the saturated hydraulic conductivity, where your field data is going to be messier. There's going to be other things going on that aren't controlled for in the HYPROP.
I think there are some things that you have to think about for the QA/QC of your data when it comes to doing in situ retention curves. The response time of the 2 different sensors might vary a little bit, so that you might need to do some cleaning of the data to get rid of, especially during really flashy events, like if you have a sudden high intensity rainfall event, one sensor might respond faster than the other to that. So doing some cleaning up of the data on that, I've seen some examples where people generated retention curves in situ from those sensors and didn't do any cleaning of those data. But it's pretty obvious when you see that.
It kind of brings up a good point, though. You don't have to use all 35,000 data points that you have, right?
No, you don't.
But, anytime you're plucking data points from a data set, it opens the possibility to be biased. Right? So you want to have some objective criterion in which to select what data you're going to use.
But I've seen some really interesting retention curves. Actually, I think Andres Padragani has done quite a bit of work on this himself, and he's seen some really good results from doing these in situ measurements and seen some really interesting results. And so I would recommend keeping an eye out for some of the publications that are coming out from him. And we've done some work ourselves, but I think there's more work to be done in this area, because I really think the technology is just now getting to the point where we can make really reliable measurements of
over
both.
Pretty much the entire range.
So I think it's going to be really interesting to look at that. And I'm personally a field measurement person myself. I always find that lab measurements are in ideal conditions. And so when we can tie in those field measurements, it really helps us get a better understanding of actual field behavior of water dynamics and soil.
They complement the lab measurements and not necessarily supersede it. Because you can separate what the soil's contribution is to it in an ideal condition, as opposed to what's actually happening in a more chaotic field setting with more confounding variables.
Exactly.
All right. Any final thoughts on soil moisture measurements, you guys, before we close up here?
More background data, the better. Metadata is critical when it comes, especially to water content measurements by themselves. And so have more site information to go along with that. And also reach out to us. We love talking about this stuff.
Yeah, seriously. If you can't tell already, we do. But yeah, water content, it's a hugely important variable across, any type of ecosystem.
Yeah.
It's going to be a driver of what is happening in that system, whether it's an agricultural system or a natural system. And it's going to drive everything from water, from fires to crop yields and crop quality.
All right. Well, that's going to wrap it up for us today. Thank you again for joining us, and we hope that you enjoyed this discussion. And thank you again for all your great questions. And if you have any questions that we didn't answer, please contact us via our website, metergroup.com. Finally, you can subscribe to the Meter Group YouTube channel and accept notifications to see previous episodes of Office Hours and to get notified when future videos are available. Thanks again, stay safe, and have a great day.